Hello, everyone. And I'm Irina Schreiber. I'm the global head of SIG Energy. And our group is relatively young and just starting. And this is actually our first own webinar with which we are starting our path to developing SIG Energy inside of IPMA. And during our session, you have a possibility to ask your questions in question and answer tool. You can write it as well to the chat, but it would be better if you write it directly to questions and answers. And then we will be able to look at them and react to them. And of course, energy group, as I said, we are quite young relatively, but we have to be quite energetic because in today's world, full of uncertainties, of different kind of uncertainties, we need to have significant changes in energy. And maybe some of you think that climate changing quite gradually, but if some of you don't believe in that, some does believe in that, but if we don't do anything right now and this happens to us, it will be a little bit too late to react, and we have to find a right balance between economically efficient and socially acceptable energy production and consumption and transformation, how we call it. And there is no doubt that companies and energy sectors are now really trying to see it as a carbon emission reduction and to see it as a commercial imperative, and how can we reach it? What is our primary goal, and how we come to a transformation of the global energy? And this is our first webinar, exactly the point why we created SIG Group, to unite people which are ready to discuss these issues, how to collaborate with each other, how to find a proper collaboration between financial, political institutions, scientific institutions, which we quite often forget in this area, and how do we proceed with the transformation, and how do we power our future. This is the topic of our webinar today, together with my dear colleague and friend, Hans-Peter Beck. And first of all, I just briefly remind you what is a goal, UN goals of sustainable development. Energy is goal number 7. And this is what we agreed to achieve by 2030, ensure universal access to affordable, reliable, and modern energy services, increase the share of renewable energy. And this is a nice point to notice. I'm a nuclear physicist together with Hans-Peter as well. So you probably would understand my personal complication with this goal, but nevertheless, it's important as well. And double the global rate of improvement in energy efficiency, enhance international cooperation, in which we are really good in scientific environment at CERN, to facilitate access to clean energy research and technology in all the countries, and to really promote investment into infrastructure, energy infrastructure, and clean energy technology, and expand infrastructure and upgrade technology for supplying modern energy services for all, especially developing countries. So far, so good. But this is just recently the latest summary of the UN General Assembly Economic and Social Council from this May, and where we are right now in 2023 in relations to all the goals which I mentioned previously. And we are progressing, we are getting better, but you can see still we are have quite a problem with almost 700 million people in sub-Saharan Africa, lack of access to electricity, and 71% of global population has access to clean cooking fuel. However, still exactly in the same region, we have quite some problems, and they are not yet on the way to resolve. But looking even more globally, not only in this region, but yes, we increase quite a lot a share of renewable sources in energy consumption, but it's driven by electricity. It's understandable why it is driven by electricity, of course, but nevertheless, we are behind our goals, and many countries, developing countries especially, they didn't reach this goal, but in countries like France as well, we have problems to reach this goal. But maybe it's not such a problem, but maybe we have to reconsider this target as well. We can see that the rate of improvement in primary energy intensity dropped in 2020, and it was the worst year actually since previous financial crisis. We need quite a huge improvement, which is not anymore, anyway, on the path right now. We are not there yet. 3.4% is quite big to reach, to meet the target by 2030, and probably we fail it. And financial flow is as well going down quite a lot. This trend started even before COVID, but we are degrading in this financial flow. Again, I mentioned already that, in developing countries, we are quite far away from the goal for renewable energy, but it's not only developing countries. It's quite important to understand in all these issues, to reach all these goals, what do we mean by energy transition? And many people still think about as a simple switch from carbon-based to non-carbon-based fuel, but it's much more complex than that. And we have to, as well, just timing already is a huge issue. As I showed, 2030, 2050, we're always changing that. What is our timing? How quickly it should happen? How quickly it could happen? And actually, the definition from IRENA, International Renewable Energy Agency, a pathway toward transforming the global energy sector from fossil fuel to zero carbon by the second half of this century, is more flexible. And this is on what we rely right now, but nevertheless, there are still quite some important questions we are not answering, which are raised by the public, by society, by companies. And I listed some of them, but they are not, it's far away from being the whole list, but just some of them, which I find more important. Is energy transition is happening at all? If this is needed and if it's happening, because it cannot happen overnight. It's quite a radical change, and it cannot happen from one day to another. And many people still don't understand how it will influence them personally and how it will influence their companies, this energy transition. And there is a huge belief that energy transition can mirror technological development, which is not true because, for example, fossil fuel, just one of the reasons, fossil fuel, which powers up our devices, it's also used as a feedstock for modern technologies, for modern products. So we cannot just simply change from one to another. And if you think in numbers, we were using around 91% of fossil fuel in 1980. Now we are 40 years further and we are still using 80%. So the transition cannot be that quick. And will we achieve net zero by 2030? I think this question is answered already, that by 2030 we won't manage. But would it be feasible by 2050? What we have to do and how we have to change our system to at least come closer to that by 50. With the modern policy along that, I don't believe we do that, and especially policy which was raised against of nuclear, some countries stopping nuclear. My personal opinion that even 2050 is not likely anymore. But it's an important question to ask. Very important question for many, just people outside the society. Electrical vehicles, we are talking about that all the time. We are replacing our standard vehicles to electrical vehicles. By 2035, we agreed in EU to stop the production, as far as I remember that. But it means that by 2030, we need 60% of electrical vehicles on the streets. But still, this production requires, I mean, remember batteries, yeah, we do require them not only for vehicles, for all our electricity system, for all our renewable energy. Rare earth elements, China has a monopoly, almost a monopoly on that. And Western nations, we don't really easy agree to open new mines. Where do we get these elements, which not only needed for vehicles, which are needed for other electronics? We need it a lot. And where do we get it? Do we manage on such a simple thing as just vehicles? Carbon taxes. This morning, I started to read an article. First thing in the morning, I read an article about carbon credit markets. Will it really help us to reduce CO2 emission? Or maybe it will help us, but by the cost of living standards? Or maybe we just start to resell these credits? How essential and how efficient this measure? And the most important for me is clean energy. Do we need clean or green? And for this, I will really briefly show you the data. This is a carbon intensity on electricity consumption. This is just electricity. I would like to remind you that electricity is around 30% of the total energy consumption. So electricity, Sweden, gray bar is the UK target by 2030. So Sweden, so far so good. France, which didn't reach 2020 goal in renewable energy sources. They fail it. They're quite good. But what about Germany, who just closed all the nuclear power plants? And Australia as well down here. The worst is Poland, but this is clear. A lot of coal had to be used this year in Germany as well. If you want to look on the more precise numbers, it's here, the same carbon intensity, and you see the intensity in countries like France almost 10 times lower than Germany, and you see where it comes from. And Australia, if you look at that region, which is using the renewable energy the most, I would say, Germany as well inside of Europe, but still very high in carbon intensity. What is the right way to energy transition? And we do understand it already that energy mix certainly will change, and we try to reduce our carbon emission. All countries trying to do that, but what speed we need, what magnitude, which sources we should be using, what should be the proper way to do that, and how fast realistically it will happen, and how we have to change our targets, our goals according to that. And this is what we are discussing today, and I'm happy to introduce you my colleague Hans-Peter back and give him a stage to talk about his view, how we can power our future and what do we need for that. Hans-Peter, the stage is yours. Thank you for being here today.
Thank you, Irina. Thank you for introducing the topic, the subject, and making clear why it is important. So I'll try to, I cannot share, so again. Share screen. So my name is Hans-Peter Beck. I'm at University of Bern. I'm a professor at University of Fribourg. I'm working together with Irina at CERN, so that's where we mostly meet. And if you look down here, the IYP-SSD, this stands for the International Year of Basic Sciences for Sustainable Development Goals, which last year and this year is the UNESCO year of basic sciences for sustainable development goals, because it needs the basic sciences that energy transitions and all the other sustainable development goals can be met. Without science, nothing works. Let's step up with what Irina just been saying with the energy transition. And here I say, Houston, we have a problem. The well-known phrase from the Apollo mission, it got solved, and we will solve it this time as well. So what do I mean with the problem? The problem basically is climate change, climate warming. And for this, I would like to remember you the 2021 Nobel Prize in Physics, which is work on complex systems, which includes Earth climate. And it's about climate modeling. I don't want to bore you with the technical details, but Giorgio Parisi is the guy who learned how complex systems can be formulated into emerging numbers to understand, who are easy. If you think about something that everybody can understand, if you think about gas molecules in a gas, every gas molecule has a very chaotic, momentary way to go and bumps into others and does this and that. But in the end, describing gas, you do not need to know every single molecule. It's sufficient if you know temperature, pressure, and volume. And then you have basically understood what the thing will do with you and what you can do with the gas. That's similar with a complex system like we have to understand climate, meaning weather is the complicated part, but the climate is the emerging, averaging out value, which can be understood. So the message here is that also complex systems can be tackled vigorously, scientifically. Also, climate is such a complex system. Understanding weather is more difficult than understanding climate, way more difficult. And those who have shown how this works, Sukuro Manabe and Klaus Hasselmann, they have made crystal clear that how physics modeling really tackles Earth's climate and quantifying it in a proper way, which could be proven over the last 30, 40, almost 50 years. With the Nobel Prize of 2021, we have a crystal clear scientific consensus what drives Earth climate. This is basically solid and not any more questionable. Of course, science is science. We do have refinements, we do have improvements. This will go on because the scientific process never stops. This is similar as if you understand Earth is flat or Earth is round. Of course, Earth is round, we all know. But then you can go further and then can make Earth is oblate and has some tiny structures, etc., etc. This is a scientific progress. It does not change the global picture. That's the important message to take above here. And we can look back. Irina has been mentioning CO2, and we all hear about CO2 when we read the news, when we look up what's going on in the world. And I have here two plots. And the left plot shows the CO2 level in the atmosphere over the last 2,000 years, which can be reconstructed out of tree rings. You can do isotope analysis of old trees, and you find very accurately what's going on in the last 2,000 years. And you see CO2 hasn't moved in the last 1,800 years, and only with the Industrial Revolution, we do have a strong rise of CO2, which from 270 parts per million is now way above 400 parts per million. So it's not yet double, but let's say 60, 70% more than it used to be. Then you can say 2,000 years is not long enough. We want to look further, and we can do that over 800,000 years in ice core drillings and looking for enclosed air bubbles in ice cores that you find in Antarctica and Greenland. And you go deep in your drilling to isotope analysis. And what you find, CO2 has been going up and down over the last 2,000 years, which is understood why this happens. Because this is how the Earth orbits around the Sun. And sometimes it gets a pull from Jupiter, a pull from Saturn, etc. And the way these big planets rotate around the Sun and pull and push Earth, this leads to these so-called Milankovitch cycles, responsible for warm ages and ice ages, etc., etc. And we saw also this reflected back then in CO2. But this is unmatched with what we have today, which even at the highest peaks in the past are 300 ppm, now we are way above 400. This is the extra CO2 that we have been drilling out from fossil fuels, drilling oil and mining coal and burning it and letting it go into the atmosphere. You can go further back than 800,000 years, and you can go to very old ages. There we had higher CO2 values in the atmosphere, but also different climates. So high CO2 values do not mean the end of the world. It just means a completely different world. one that we may not be good living in. Temperature, and this plot from 18 showing the average global temperature. It's not the temperature in your backyard. This is the averaged out global temperature. I'm showing that from 1850 till today. And you see every year has a new value, goes going up and down, but you see a trend. And the trend is strongly going up. Let's say from 1980 to today, you have a huge gradient of global warming. And this correlates well within the climate models. The climate models can exactly model exactly this. What does it mean, global warming, driven by CO2 emissions? First of all, to understand, global warming is not uniform. It doesn't mean everywhere it's 0.5 or 0.7 or 1 degree warmer or not. Global warming means there are places where you heat up a lot. The polar region, they will heat up to 7 degrees above their usual value. Meaning at the North Pole, it's minus 50 degrees. Now it's minus 43. And they think it doesn't matter, it's still cold. But these 7 degrees will push further. They will move the cold air down. It means that inhabited areas in the northern areas getting extremely cold from time to time. So global warming may cause cold fronts. They also do called heat waves. Heat waves and droughts called wildfires. Global warming, the atmosphere is warm. It can carry much more water in the atmosphere. So this leads to extreme rainfall, which means flooding. But heat waves means droughts. So you have flooding, rainfall, droughts all together, but not at the same place, not at the same moment. Droughts, they mean harvest failures and losses. This leads to famine. Global warming at the polar region, and I'm talking about Antarctica because the North Pole floats. The ice is floating on the water, but in Antarctica, the ice is on rock. When that melts, we do get a rise of sea level, which means that coastal cities are becoming inhabitable. Not today and tomorrow, but for our children, for our grandchildren, will become a problem. With this, we create mass migration because all the coastal regions become inhabitable. And in the end, with famine and inhabitable coastal regions and mass migrations, this could well mean a global collapse of society. It's not a localized collapse of society, which we see in zones of war or in zones of famine, in zones. This is isolated events, which are tragic, but not global. But we are heading towards a global collapse of society. Not today, maybe not for our generation, but the coming next generation. This will be what they're aiming at. But to say it's not the end of the world. It's the end of society, the way we live, the way we know living. And it's not just us as human animals, it's also for many other wildlife in the biosphere. Good. Understood that thing. We do need to decarbonize the world in the atmosphere, which is the climate. We have to fight the climate crisis because I see it as the biggest threat, more than pandemics, as we have seen with COVID, more than wars, because wars, they tend to be regionally bound. They are very bad and very strong problems and costly and nerve-breaking in all kinds and a real tragedy, but not a global problem. In the global problem, we do have climate. Let's see. Irene was talking about CO2. I'm much more talking about greenhouse gases because CO2 is a greenhouse gas driver, but there are many others. Methane to talk about, or ammoniac, or many other stuff which is really heating up. In that sense, whoever's talk about CO2 tax, it may be too narrow-minded. If you replace CO2 then with methane, you have to gain a bit. So this is something to take back home. Think about greenhouse gases and not just about one specific of those driving gases. Greenhouse gases, they get into the atmosphere when we produce energy. Producing energy means we're producing electricity, we're producing heat, and we need energy for transport. This is 3/4 of the amount where greenhouse gases are coming from. Iron, steel production, etc., mining is 24%. Transport about 16% globally, which mostly is on the road. If you think about air and ship traffic, this is below 2%. Of course, airplanes are bad, but there are relatively few on the planet, and there are many more cars on the planet. So if you put all your energy to reduce air traffic and make it more clean, you haven't gained a bit. But every measure you try to do, focus on the big numbers first, focus on the drivers. That's here the message. Buildings, there are 17.5%, which is residential buildings and commercial buildings. This is heating the buildings in winter and cooling the buildings in summer, both. So that's, I don't want to go into detail to everything. The global amount of energy that we used in 2019, that's the number I have, 170,000 terawatt hours of primary energy produced and consumed in 1 year. And if you look at that primary energy, 80% is from gas, oil, and coal. If you add traditional biomass is burning of wood, deforestation. Together we get to 85% of primary energy is CO2 intense. This 85% we have to fight, but we still need energy. We will need that amount of energy now and even more so in the future. Even if we're becoming more efficient in doing things, don't think about that we will need less. I think that's an illusion. We do need electricity. Primary energy is all energy that we need for heating and for transport. This, which is 170,000 terawatt hours. These 30,000 terawatt hours is just the electric power. And then to almost 2/3, to 62%, electricity is produced by burning coal, gas, or oil. Oil is a little bit just 3%, but these are the CO2 intense way to produce electricity. Those have to go. If you look what are the others, we have bioenergy, solar, wind, hydropower, nuclear. They are all at the 10% levels, with hydropower, with 15%, quite good. Primary energy, we may go down, but the electricity production is expected to double by 2050. And I think that's a modest assumption. We have to reduce fossil fuels, and we have to electrify basically everything. Transport has been mentioned by Irina, but also production. We have to produce steel by electric means, not by burning coal. And that's a technological challenge which can be solved, but it's not yet there on the market, or not in big scale on the market. This will lead to green steel and others. Producing energy, producing our modern world, we rely on all kinds of goods and materials that we are mining from the earth crust. And on this plot, I'm showing how much mining has increased in the last 20 years from 2000 to 2018. These are the dates I've been finding, but it's relentlessly continuing even to today, 2023. Coal has increased by 2/3. Fine. Gas has increased by 60%, oil only 26%, which is fine. But industrial minerals has more than doubled. It's now 144% more in these 18 years. Precious metals, or base metals for World Bank, all days they're double. So we have an increased need for all kinds of materials, including lithium, copper, nickel, neodymium, and all kinds of rare earth metals that are mined more and more. So the mining companies, they have a great time because they're in big demand. If you look about what does energy do, and here in this plot, I'm comparing energy use and gross domestic product. And if one looks what is the gross domestic product per capita in a country and how much CO2 has a person emitted in a certain country, you see that we do have energy poor countries, but when they are energy poor, whatever they earn in low numbers between $0 to $10,000 per year, they are not big users, big emitters of CO2. But as soon as you're above a certain threshold, as soon as you're enough rich, you're becoming energy hungry. And the worst is here, Singapore with a GDP per capita of $100,000, but 20 tons of CO2 emitted per person in Singapore. Well, Singapore is a very small, very tiny spot on this planet. It is not a big driver, but it's a showcase. The richer you are, the more CO2 you release, and this has to curb. You also have here pointed out the United States or Canada, which are big. China, which is often blamed as being very bad in CO2 emission. Yes, because it's a big country. It's more than 1 billion people. But per capita, it's just at the transition out of energy poverty. Not to be confused. So if you're rich, you emit too much CO2. It strongly correlates CO2 and GDP per capita. It is the high CO2 emitting countries, which are the rich countries, that have to drive what to do, how to place. But whatever they do, it must stay affordable also in low GDP countries, whatever we do for energy transition, because we cannot deprive low GDP countries from developing further, from tackling their own problems they have. And in the end, if you have too many poor people, think about China, even if they're per capita low, in mass, they are big. It needs energy to find and provide better solutions, how to produce and use energy without CO2 emission. Producing electricity CO2 free. What are the options we have? Because it must be available 24/7. It must be abundant. It must be cheap. Let's see. We can produce electricity by burning coal. Lignite, this is black coal and brown coal, and or by burning gas, or by burning gas and doing carbon capture and storage. You see that whatever is coal and gas based, we have 870, 820 grams of CO2 per kilowatt hour electricity produced. So when you have your Hoover running for 1 hour in your apartment, that's the equivalent of releasing 800 grams of CO2 into the atmosphere. Then what are the CO2 low options? You see nuclear, 10 to 20 grams. This is not from the burning of the nuclear fuel. This is from the construction of the sites and of the mining and etc., the transport that is needed. We do have hydropower, 5 to 15 grams per kilowatt hour electricity. Wind power, 5 to 30 grams, depending on where you place your windmill and how efficiently it's being used. Solar. People think solar is CO2 free. Honestly, it's not. It's not bad. 35 to 104 grams of CO2 per kilowatt hour produced. This is mainly in the production of the photovoltaic cells, which is high intense, energy intense to produce solar panels. Burning wood releases CO2 in the atmosphere. And then biogas, 150 to 450, because biogas is not that, it's always been claimed is a very good option. In the end, it's not so good. Leave the biosphere where it is. That's my comment in here. If you're a country, if you have to think, I need from my country so many thousand terawatt hours of electricity annually. How do I produce that? You can look, what are different plants giving me? I can look about the nuclear power plant, a typical one. an average size power plant, if it's a nuclear power plant, I get 13 terawatt hours out annually. Out of a typical size coal plant, about half, 7 terawatt hours annually. So with this, I have a good harvest per year. With an average size gas plant, 2 terawatt hours, or a hydroelectric plant, this is a dam, storage dam or river dam, depending, it's average size. So they are bigger and they're smaller, but 1.3 terawatt hours is a typical average hour. Then you can look about an array of solar photovoltaic cells. An industrial size array typically produces 33 gigawatt hours annually. And this is gigawatt hours compared with terawatt hours. There's a factor thousands in the unit. So one has to be careful. To look about what that means, to produce 1,000 terawatt hours per year, you need 30,000 industrial scale solar photovoltaic arrays. Or you need 12,000 wind turbine arrays. You need probably 750 hydroelectric plants. You may need 140 coal plants, or you may need 80 nuclear plants. I was figuring out what the number is. So 1,000 terawatt hours, to give you a comparison, this is what Brazil, as a big country, assumes really need by 2050. Think about wind. Wind is good because wind blows for free. That's and wind produced globally about 1,270 terawatt hours of electricity in 2018, and we are 2023. So this number has increased. I have to look up what are the latest numbers. It's about 5% of the global electricity production, and a single wind turbine is 8 megawatt peak. But 8 megawatt, this is power. This is not energy. Never confuse the units. Whenever you see that, think about: are you talking about power? Are we talking about energy? That's really important. The big problem with wind, it is very intermittent. And you think if I have many windmills, then they average out and I have constant power. That's something that people think, and it's just wishful thinking, because wind is a large-scale phenomenon. You have the big wind directions globally. And when they go, you have huge areas that either have wind or do not have wind. And then you have to think about areas and times when the wind is not good enough and your power production is very low. And I have numbers from Brittany. In a typical winter, they have about more than 2 weeks when the 1,600 windmills together, all together, produce less than 10% of their capacity. It's not a few that are low going. All of them are low going because wind is a large scale phenomenon. Or sometimes you have days where they do not work at all with less than 5 or less than 2% of the energy they can have. So harvesting can go up and down in a strong way. So you have to have backup solutions in times when there is no wind or not enough wind. A windmill lives about 10 years to 20 years, depending how complex you're producing it. Because wind is constantly erratic in its behavior, and this results in huge strains on the blades. So here, this area, this is at maximum strain. Especially think about an 80-meter blade, and then a huge windmill. Here's an offshore one. The strain that you have is way more than what an airliner has on a transatlantic flight, and you go into a turbulences. And sometimes you are afraid when you see the wings moving. So, of course, then you have a trade-off between lifespan and price of the windmill. So you have to choose what is optimal. Cheaper ones with 10 years lifetime, so more expensive ones with 20 years of lifetime. They are very non-trivial for maintenance, especially when they're offshore, because boats and helicopters to do maintenance, they need good weather to go there and do some. So you may have prolonged periods where you cannot do any maintenance. You cannot reuse nor recycle many of the components in these windmills, and after 10, 20 years, you put them into dumps. And this is okay if you have few windmills. This becomes a problem if you have many. We always talk about endangered wildlife, birds and bats. They are copiously killed. And then you say yes, but cats kill many more birds annually. But they also say yes, but the windmills stay still and kill the big and rare species much more often than cats can do. So think about not just the average numbers. Think about the big and rare species as well. Solar power. Here you see a solar power array on the grid. And on the plot here that I'm showing, this is the years of the month from January, February up to November, December on the Northern Hemisphere. So I think this is somewhere in Germany. And you see that the solar panel works nicely in the months of June and July. But in January, February, November, December specifically, they almost deliver. You get about 10% of what you need. So in order to profit from photovoltaic cells, you need seasonal storage capacities. And whenever people talk about how cheap photovoltaic panels are and how cheap electricity produced by solar power is, yes, that's correct. At the moment when they produce energy and you have use for that energy, then it's cheap. But you still need the backup solution to survive winter. And for this, you need seasonal storage capacities or a complete independent power production network. So you have to double almost your system in order that people can survive winter. So this extra burden is never mentioned in the cost estimates. And that has to be very, very careful. A few thoughts about the solar power. Lifespan, 20 to 30 years. But only when they're only useful when the sun is high on the horizon and shines bright. The problem with electricity, it cannot be stored at large scales. And if you look at this place here, this photo I'm showing here, you need huge areas to have a decent amount of electricity produced. My conclusion out of this, solar energy is green energy. But the solar panels themselves are not, because they have to be manufactured. To manufacture a solar panel, you need super pure crystalline silicium. And to produce super pure crystalline silicium, you have to melt silicium oxide and evaporate all the oxygen in it, and then let it cool down in a very controlled way so it can crystalline in a way that it works out. This you have to do over prolonged, many, many hours or days at 2000 degrees. Only coal plants today can do that. And it's done in China, predominantly on the world. You need a hell lot of toxic chemicals and rare earth metals that you have to mine for. And you produce a lot of waste because the lifespan of those is 20 to 30 years. You have to replace them. The International Renewable Energy Agency, IRENA, estimated that in 2016, about 250,000 metric tons of solar panel waste was there in the world. And this would go up to 80 million metric tons by 2050. These are non-negligible numbers because these panels, they contain lead, cadmium, and other toxic chemicals that cannot be removed without breaking apart the entire panel. If you would like to harvest and get out lead, cadmium, and other stuff, it's a highly industrialized, energy intense process. And if you do that, then you have lost all the advantages. 90% of the photovoltaic modules are made out of glass, but then this glass cannot be recycled well as flow glass, so it's really ditched. we will get big amounts of lead, cadmium, antimony. These are driving elements that will end up in waste dumps. Talking about waste dump, talk about the material that we need by energy source. On this plot I'm showing is how many tons of materials do I need to produce 1 terawatt hour of electricity. And I'm doing this here for solar photovoltaic panels, for hydro dams and a hydro river, for windmills, for geothermal plants, and for nuclear plants. And you see the material I need, which is cement in blue, concrete in gray, glass in light green, the fuel that I burn in orange, the steel that being used, and other yellow. Other, think about rare earth metals. Think about what you need in a windmill, all the to produce the permanent magnets that you need in there or all the reinforcement you need that the turbine hold. You need non-trivial elements in order to do that. And look about the amount of other in the solar photovoltaic panel. This is non-negligible, and this is on the long run a problem. In the short run, we can manage. On the long run, this is adding up in a catastrophic way. So whoever says that solar energy is renewable energy has not understood or not seeing this plot. It's really not. We do need baseload power because solar and wind, they produce intermittent power. But an industry needs power 24/7, reliably, stable, abundant, affordable. This plot I'm showing here is Germany. The amount, and Germany is the country that invested the most in wind and solar energy. We have on this plot, you see 2 types of blue. This is onshore wind and offshore wind. And you see yellow peaks. This is photovoltaic panels. And this is the amount of electricity produced from mid-November to mid-December 2022. I agree, November, December, the sun is not shining bright, but the wind, they're blowing what can. Then you look at this wobbly red line on top. This is the energy consumption, the electricity consumption in Germany. And you see it's a big gap. And this big gap I'm showing here is filled by burning coal and gas and by inputs from neighboring countries. Germany has invested, if I'm not mistaken, something like 500 billion euros or dollars over the last 10, 15 years in wind and solar power. And still, they are nowhere in getting green because they have to burn a hell lot of coal. And how much coal they're burning, I will show in the next graph. This graph is a full year from 1st of January 22 to 1st of January 23, a full year. Every dot, this dot here that I'm pointing out, and the next dot next to it, and so every dot is 1 hour of electricity production in a country. Brown countries is Germany, blue is France, yellow here is Spain, gray is Poland, this orange is Portugal, and so on. What you see, and on the y-axis, you see the CO2 intensity. To producing 1 kilowatt hour of electricity, how much CO2 has been released in the atmosphere. On the x-axis, how much energy has been produced in a specific hour. And you understand, on the weekend and when everybody's on vacation, not so much energy is being used, but when the industry is high, when everybody's working, electricity needs are high. So you understand that in a country, you have a huge variety from left to right along the x-axis. because this is just the day and night and the weekend and etc. Variation that we have. And this is this for big countries. This is large variation, big needs and low needs. What you have to be careful, what you have to look about how much CO2 is being produced. Let's take France, this big blob down here. France in 2022 has been predominantly producing electricity with nuclear power, but they had some problems with maintenance and revision. So they also had to import, they also had to burn coal and gas in order to produce electricity. But this gives some variation along the y-axis, but it's a little one. Look about Germany just above France. It's a huge blob. They may have huge demand on electricity at certain moments, in specific hours, but there is no sun, there is no wind, so they have to burn coal and get a huge CO2 intensity for a big amount of electricity need. They also have at night big CO2 intensity, but at night here on the left side of this blue blob, this is during the night, the electricity needs are little, but the sun doesn't shine, so CO2 intensity goes high. Despite of investing 500 million euros over the last 10, 15 years, Germany is way worse and has not tackled at all, has not solved at all their CO2 emission problem when producing electricity. But Germany wants to electrify everything, as every other countries like to do. But when you do that, think about the CO2, because if you do not reduce CO2 by producing electricity, we have not solved the climate issue. And this is the prime driver of why we do everything. Poland, this gray blob here, also Irina has mentioned Poland before. They are burning mainly coal. Coal is very CO2 intense, so that's what they do. But Poland has made up, they will get out of coal and invest into nuclear power. And which we will see in 5 to 10 years from now, Poland getting down as good as we have Switzerland, Norway, France, etc. They will reduce their CO2 intensity by quite a lot. This is the same plot, but now fully integrated over a full year. This is fully aggregated over the full year of, was it 2020? Yes, this is 2021. This is the numbers I found. In 2021, you see Germany here as a brown country. Brown means bad on CO2 because Germany had a CO2 intensity of 481 grams of CO2 per kilowatt hour electricity produced. Compare this 481, for instance, with Sweden, just had 20 grams of CO2. This is more than 20, this is 25 times the value. Because Sweden is basically hydropower, nuclear, and some wind. Poland, with 820, just burning coal and gas. And Germany, who has been invested a hell amount of money in solar and wind, is still at 480 grams. And if you look about how much was Germany is relying on fossils to produce electricity, you see that the amount of electricity produced in 2020 was 235 terawatt hours of electricity was produced by burning coal and other fossil fuels. And this increased by 2021, increased further by 2022. They were decreasing before, but now they reached a level where you can no longer can decrease. It's going up again. And this is something really to understand and look up. Look at the green countries or France and say they are low on CO2 intensity when producing electricity. That's where the world has to aim at. I mentioned we do need storage. We need storage to make wind and solar energy usable. People are talking about batteries. Yes, you can store electricity using batteries, but think about the cost. The costs today are in the order of 1 million or euros per megawatt hour of stored energy. Think about the scale. You need about 50 square meters per megawatt hour of stored energy. This is here with Tesla batteries. That this is a Tesla battery plant that I'm showing here. I know the numbers for Switzerland. Switzerland wants to, if Switzerland would like to survive winter, Switzerland would need a storage capacity of about 10 terawatt hours. That is harvested in summer and then used in winter. And if about half of the electricity in Switzerland is produced by hydropower, so this is just for the other, we include the hydropower. This is just, if you would abandon nuclear power in Switzerland, then we would need to increase solar and wind, and we will need to have 10 terawatt hours of stored energy capacity. If 1 megawatt hour costs $1 million, we need something like $10 trillion to do that. Switzerland has 8 million inhabitants, which means about $2.5 million per capita to realize this amount of battery storage. So it's extremely expensive, unless a major new technology would arise, but this is not on the horizon. Think of a few percent better, think about 20%, 30% increase, but not orders of magnitude. And then not enough lithium in the world. So battery storage is not a viable option for the world population. We do have small-scale plants. Here I'll show one, and it's justified in areas where costs are not the limiting factor. You can store electricity by pump lakes. You can pump water from a lower lake to an upper lake. That's fine. This is done in Switzerland. And I show here a recent example of a new pump storage plant installed in Switzerland. It did cost $2 billion or euros. It can store 40 gigawatt hours of electricity. Gigawatt hours, not the terawatt hours that we need. That's a factor 1,000 between gigawatt and terawatt. The costs get down to $50,000 per megawatt hour stored. Way cheaper than batteries. But still, for the 10 terawatt hours that we need, 500 billion euros or dollars, which means in Switzerland, $60,000 per person, which is a lot, which is 1 year of GDP of most countries. But we would need 250 such systems in addition to what we have. And you do need 2 lakes, a pump lake and a storage lake, and infrastructure between. And such suitable topologies and lakes cannot be found in Switzerland. And in most countries, they do not even have enough mountains to do that. So think about in Germany, completely an illusion that something like this would be possible. Good. So batteries are out. They help, but are out. Water storage, it helps, but it's out. Not the big solution. Let's think about hydrogen. Everybody's talked about power to gas, power and producing hydrogen. This is cool. Everybody wants that. We can electrolyze water with a high efficiency, 70% efficiency or even higher. We can, today it costs about $10 per kilogram of hydrogen. To do that, we can go down to $2 per kilogram. But then you have the hydrogen. Then it's getting really complex because hydrogen is a gas. To store it, you have to liquefy it, but it boils already at 20 Kelvin. This is, let's say, minus 250 degrees Celsius order of. It's really complicated to cool hydrogen to that low values, and that's energy intense. You don't get that for free. If you don't want to liquefy it, you can pressurize it. You can pressurize it to 300 bars, 700 bars, so 700 times the atmospheric pressure. With this, you get the energy density at 700 bars of 2 megawatt hours per cubic meter. But what you have in your hand is a bomb. It's a real bomb. Then you have to use this liquefied or pressurized hydrogen. You have to make power to gas out of it. Then you get synthetic fuels. Or you can use hydrogen directly in a combustion engine or in a fuel cell. All of this has its own efficiency level. That's all fine. In the end, green hydrogen offers potentials, but it's really expensive. You can take expensive in terms of dollars per kilowatt hours, and you can think I can get dollars down with better technologies. Maybe yes, but it's expensive in terms of energy that you put in versus the energy that you get out. You put a lot of energy in and you almost get nothing out. Think of a total cycle of 10, 15%. 85% of primary energy is wasted when you go to use hydrogen. But still, hydrogen will be used. It is an important gas. It will be used where there is no option available. And I could think about aviation, heavy goods transport, steel production, cement production, manufacturing. There will be many use cases, but it's not to survive winter. This plot here shows the difference between energy density and costs of petrol or alcohol, which is very, very good, versus what you put in a battery. It's very heavy, very low energy density per weight and very expensive. So to be viable, economically viable, you have to be in the lower right corner. Synthetic oil has the same energy density, but it's more expensive. Liquid hydrogen is even is good but expensive. Possible, but it's then think about the energy in, energy out. But then what's wrong with hydrogen? Hydrogen has even more problems. Because hydrogen itself cannot be stored, cannot be transported without considerable losses. The hydrogen molecule is the smallest molecule imaginable. It diffuses through every container. In a good and expensive master container, you think about losing 0.1 to 0.2% per day. But most containers on the market are being used, they are losing up to 3-4% per day. Then, so you have to produce more hydrogen that you're going to use because it boils off. But then hydrogen goes into the atmosphere because it's not being burned. Burned hydrogen is fine, that's not a problem, it's getting water. But atmosphere per se in the atmosphere reacts chemically in the atmosphere and will help building up more greenhouse gases. And per kilogram of weight of hydrogen compared with CO2, it is 11 to 33 times more effective in heating up the atmosphere. So we have to be extremely careful with hydrogen. We have to, when we produce hydrogen, we have to use it immediately, not storing it and not transporting it. And this is the paper for it with all the details and the numbers that shows that this value GWP 100 is the greenhouse warming potential over a period of 100 years. We get a factor of 11 where hydrogen is more dangerous than CO2. Or GWP 20 is the greenhouse warming potential over a period of 20 years where we have a factor of almost 33 where hydrogen is more effective over CO2. And this comes from UK governmental studies, and you have the link to the full paper. So to me, but also to Irene, we shall not forget about nuclear. And I think there is now a renaissance finally coming up. People are thinking it is dangerous. And those who are working in nuclear areas, nuclear fields, they say it's safest and cleanest. In this plot that I'm showing here, this is the death rate per terawatt hour of electricity produced. Coal has about 25 people killed per terawatt hour of electricity produced because coal has to be mined and has to be transported. That's one part of it. But think about all the air pollution that coal plants do, all the fly ash that are nocive to our breathing system, to our lungs. This kills about 25 people per terawatt hour produced. Germany has been abandoning nuclear power plants and this increased use of fossil fuels. you can Google and you find values, how many people this kills per year in extra. Burning oil to produce electricity is a bit better because you can burn oil a bit cleaner than you can burn coal. So you get down to 18 people killed per terawatt hour electricity produced. Then go down. Hydropower, this is river dams and storage dams, 0.02 deaths, and nuclear energy, 0.0 deaths in this plot. Almost nobody dies from nuclear energy. And these numbers includes all nuclear accidents that ever happened on this planet. Also, wind and solar is not death-free. Windmills have to be produced, transported, put in place. The same with solar panels, have to be installed on the roof and everywhere else. So this is a level of accidents, and how many accidents there are in the real estate. This leads to small numbers. But then it's not just the death that you have to look at. It's the greenhouse gas emission per terawatt hour electricity. So coal is a killer. People die, and pumping a hell lot of amount of CO2 into the atmosphere. Per terawatt hour, 820 tons. Oil, 700 tons. Natural gas, 500 tons. People are saying that natural gas or liquid gas is a big improvement over coal. It's a little bit of an improvement, but it's not really a game changer. We are still pumping a lot on way too much CO2 in the atmosphere when we improve, so to call, from coal to natural gas. We haven't improved much. Hydropower, 34 tons. This is mainly from the construction of the cement and concrete to build the dams. Nuclear energy, about 3 tons. Wind, 4 tons, solar, 5 tons. So this is from a CO2 point of view, we get a clear winner in the nuclear energy. So it is not a killer. In contrary, it's one of the safest we have. But then people say it's very expensive. This is a plot I have from the Swiss Federal Office of Energy. So that's an official source. They show how many cents does it cost to produce a kilowatt hour of electricity. Solar between 10 and 26 cents per kilowatt hours today. And the gray bar means by 2035, they estimate it will go down to 5 to 18 cents. The same for biogas or wind is competitive with 10 to 15 estimated. Hydropower, 7 to 30 cents. Hydro river, between 14 and 33 cents. Gas, 13, 14 cents. And then nuclear, 5 to 12 cents per kilowatt hour. So that's really a competitive. Of course, you have to build the plant, which is expensive. You have a huge investment. But then these things run over a long time, 50, 60 years, and produce a lot of energy. And then if you do the cost estimate, the costs really get down per kilowatt hour. What do we gain? A kilogram of nuclear fuel, of uranium fuels, 1 kilogram. That fits in a coffee cup because the uranium is very dense. In an espresso cup, you have 1 kilogram. This is enough electricity for one person in Europe for his or her entire life, 80 years. And we have enough fuel for the next 100, 200 fuels. And if you use the fuel correctly, for the next 1,000 years. This also means the waste that we produce over the lifespan of a person is less than 1 kilogram. And this waste can be handled because as people who work in nuclear sites, they know the nuclear power is the only source of power that we have that has a proper waste management. Coal plants simply blow the waste in the atmosphere or ditch the fly ash goes in the atmosphere, bottom ash goes into some dumps. And think about per plant of 2,000 tons per day. The waste should not be buried, but can be reused and burned away. And this way, we really have energy enough for the next, let's say, 1,000 years at least, and with new technology for the next 30,000, 50,000 years. So a nuclear plant does not radiate. Everybody is afraid of radiation. It really does not radiate. Coal plants radiate much, much more. The radiation is shielded within less than 1 meter of water, for instance. Even if there would be no shielding, if you would remove all the shielding around the power plant, radiation would not go further than about a few hundred meters in air. And this is also true for all the waste it produces. But avoid inhaling and eating radioactive isotopes. But this is the same with all other industrial wastes that we have. Don't eat the cadmium, the lead, and the antimony, etc., that comes, and all the chemicals that we bury and dump in whatever plants across the globe, in huge quantities, by the way. I don't want to go into the, I want to save some time, but we do have ways to improve the nuclear reaction chain in a nuclear power plant by shooting in the particle beam. And with this, we can use uranium waste as a fuel, producing thereby energy, or not just relying on uranium, but also on thorium. And thorium is very abundant, cheap, and globally available, which means 30,000 years of support of supply for all humanity. Because when you do so, we can reduce all kinds of long-lived decay products. That's what people are afraid of. People always say 100,000 years is the time we have to wait. The number is correct. But the danger, the real danger, is the first, let's say, 300, 400, 500 years. After that, you can approach the dump as close as what you really have to eat it that becomes dangerous. Radiation is contained. It's not something that goes big scale. Small modular nuclear reactors are big on the market because it's a fast way to power a city. These are small plants. You buy them directly from the company in a standardized way, and this is what is coming up now. And many countries are very much interested in this from-the-shelf power plant that you simply buy for relatively low cost, because everything is standardized in a maximum way. And with this, you buy one for relatively cheap money, power a city for good. Still, people are afraid of radiation. Is it as dangerous as thought, or is it panic-driven? And yes, there are dangers. We have to face dangers, but you have to face dangers whatever we do. The question is, how big are these dangers? Think about uranium, thorium. These are relatively abundant elements in the atmosphere, and we eat them every day. In the soil, we have about 0.3 to 12 milligrams of uranium per kilogram. The farmer that farms crop and wheat, and then we make bread out of it, there is uranium in the bread that you're eating. In small quantities, you don't realize that it doesn't harm you, but you're eating uranium every day. It is more abundant than antimony, beryllium, cadmium, gold, mercury, silver, tungsten, etc. So it's really a lot on it. But thorium is even more, 10 times as much as uranium. Also this you're eating every day. Potassium you're eating every day. Every banana that you're eating gives you a radioactive dose of about 1.1 microsievert, which is about 1% of the average person's daily radioactive intake. A human body, with the amount of potassium that you have in your body, you have about 4,000 radioactive decay per second in your body. Every one of you, every one of us, we are radioactive sources. We radiate with 4,000 decays per second just from the potassium, and there are other elements in us, carbon-14 and radon, etc., etc. I want to skip this part, but I want to show you how radioactive is the seawater globally. Uranium-238 in the global sea, there are 37,000 petabecquerel. A becquerel is 1 radioactive decay per second. Petabecquerel is 10 to the 15. 37,000 is a huge number. So the sea is really, really radioactive from the uranium, and even more from the potassium. Look at this number, it's another 3 zeros more. And then you think, when we were doing all the nuclear weapons tests in the 50s and the 60s, about 400 petabecquerels have been produced in addition and dumped and released in the atmosphere, and it went into the sea and the soil everywhere. So people are afraid of that naturally. Don't go to a huge amount of it, but compared, diluted in the sea, it's peanuts. It's really peanuts. You have to compare the number of 400 with this 37,000. Or compare this 400 with this 15 million. So we did not change the radioactive content of the seawater in any way, in any measurable way. Chernobyl, even less. Fukushima, even less. 3 Mile Island, even less. So think about, Earth is a radioactive ball that we live on. Radiation is natural. Care is needed, but panicking does not help, because radiation is really, really deadly at high dose rates. But it is around us all the time, everywhere. It's completely harmless at low dose rates. And every living cell on this planet, every plant, every fungi, every animal cell, and all your human body cells, they know how to handle low doses. It's so effective that it is not necessary for us to sense radioactivity at all. We do sense, our evolution has driven us to sense danger. When something is hot or spiky, we realize that and we become careful. So these are something that evolution has driven, that we have to be really careful. We do not have any evolutionary means for radioactivity because there's never been a danger. But at excessive dose rates, it becomes dangerous. You really can get killed if you get a full dose rate of 30 sieverts. You die within a day, 1 or 2 days. Or if it's just 1 or 2 sieverts, you will die with some 5% probability within 6 to 8 weeks. So that's really tragic. But no conclusive health issues can be reported at instantaneous whole body absorbed doses of 100 millisieverts. So 1/10 of this one. And we do not have any conclusive source that this would be dangerous. It even the other way around. Many indications claim that moderate exposure of low dose may be even beneficial and reduce cancer rate. But the discussion on this is not yet finally concluded. The effect of that is that regulators define radiological limits as low as possibly achievable. And I say, not only I say that this is counterproductive in many ways, but that's a different discussion. So be careful with high doses. They are dangerous. Don't worry about low dose. They may even be beneficial, but don't think that the conclusion is final on that. How do people live?
Yeah, right.
Yeah, sure. Yeah, I'm almost done. So we have no symptoms of low dose. There are places where people live with natural radiation sources around because they live on a uranium-rich soil. In Iran, is the famous city is Ramsar with 200 millisieverts per year, whereas a typical European has 4, 5, 6 millisieverts annually. So this is 40 times more. When you're a flying person, a pilot or a stewardess, a flight attendant, 7 millisieverts per year. If you live close to a nuclear power plant, you get an extra of 0.001 annually. Or if you do an X-ray, you get 0.2. or if you do a full body computed tomography, you get an extra 10. Fine. This is good. So conclusion, take home messages. I'm done talking. Providing fossil-free energy is an absolute must because the climate crisis is real and the danger for society are enormous. Energy must be available abundantly, 24/7 and affordable. And this in high and in low GDP countries. Because without energy, major problems can't be solved. And think about environmental problems, pollution, food, water, health, etc., etc. Solar and wind, they do provide electricity where the sun shines and the wind blows. But solar and wind are intermittent. Stabilizing the electric grid and providing energy at the needed capacity also at night and over all seasons is far from trivial. Expensive storage systems are needed where battery and hydro storage systems don't scale up to the needed values. Green hydrogen power to gas can help, but efficiency is very low and the price will go up. Solar and wind energy is green, but the solar panels and the windmills, they are not. They are energy intense and toxic manufacturing processes behind. Waste management, when panels and mills are replaced, are not solved. New technologies and better recycling will mitigate these problems, sure, but increases costs and reduces the energy return of energy invested into solar and wind plants. Nuclear energy is important and must be part of the energy portfolio to provide base power at all times. And the waste problem is not a real problem as it can be solved. Solar and wind have high potential to create electricity, but electricity must be used when produced as it cannot be stored at the abundant quantities we need. Especially in winter, and especially when heating will be with heat pumps, as everybody is proposing, we do need a lot of electricity in winter. And then solar won't help, as then electricity will be scarce and expensive. As we have seen, for everybody who has been reading the news this winter, everybody was afraid of blackout and the energy shortage. Demand in summer is especially high in hot countries because air conditioning will be high in demand. But here, solar energy is a good investment because it's hot when the sun shines. Green and hydrogen offers potential storing energy that can be harvested in summer and used in winter, but conversion rates aren't great. The area needed to equip with solar panels is mind-boggling. And think about the boil-off rates and the amount of hydrogen that boils off into the atmosphere. Solar panels need to be replaced after 20 to 20 years, resulting in tremendous amount of waste. So all in all, green energy comes at a high price. Therefore, keeping nuclear power in the portfolio is a must, as otherwise, as I say, things can really go difficult. Few references, and thank you for listening. And sorry for talking too long.
I see that people are still there and they're listening, and I appreciate the importance of the message. And I took the liberty to answer the questions which arrived, but there were questions about fusion energy, or question about basically has to, we have to collaborate, we have to discuss, and who has to pay? The richer countries, which are using the most of energy and producing more green gases, or those who are not producing anything. Looking at which you're presenting, who has to be responsible? How we can take care of that? I think it's more political discussion, but nevertheless, I think we have many topics to discuss inside of this SIG energy, and it can take hours and ages. We always have a topic to discuss because it's really very important at the moment for all of us. it's a quite an important change, and which we have to, which, as you said, we must to have. So I think this would be really great, guys, if you join us and follow our future meetings and webinars, so we can discuss other topics as well, because there will be many discussions raised, as many questions are raised on these topics. And participants, and I can see that the participants are still there, get the badge, IPMA badge, for joining this webinar. And if you want to follow and see the videos as well, the video from recording from this webinar will be saved on SIG IPMA website. Just look at there later. And if you want to join us, you can sign up, or if you have any questions, you can always send an email to our group, and we'll try to answer to them as much as we can, and especially that it will give us an idea what is the most urgent and interesting topic for you, and what we can do as the following events in our group as well. Thanks a lot again, Hans-Peter. We discuss it all the time, and we still have topics for discussions, and sometimes arguing, sometimes rediscussing, sometimes to get to find a common solution, how we proceed with that. So I think it's really needed to discuss from all points of view, our scientific, political, from business point of view. And quite often we are missing these common discussions. And this is what I hope we manage to organize, or at least give some steps in organizing this collaboration and communication. We are really good in collaborations at CERN, right? So to give it a new start and proceed with that. So yeah, sorry guys for taking a little bit more of your time, but I hope it was important and interesting for you. For me, it's always very nice. So I can listen this for a long time. I can talk about that for a long time. It will be a feedback proposed to you after that. It's really important for us as well to know your feedback. Please don't hesitate, and please don't skip it. And thank you for joining, and join our group and follow our other sessions. This was our first session in SIG Energy, and we'll have more, so don't skip it. I think you will find a lot of important and very valuable information.